Okay, hello everyone. My name is Shany Danieli. I'm a graduate student at Yale for the next 10 days. Then I'll be moving for a postdoc position at the IAS in Princeton. And I'm very excited to be here and talk to you together with Scott and Marla about observations of low mass satellite galaxies and low surface brightness galaxies. We have one coordinated talk. I'll start with some introduction, and then Scott and Marla will take it away. So I just want to make one note about what do we mean when we talk about low mass galaxies, as it means very different things for different people, depending on your favorite group of galaxies. All of us are going to focus on low mass galaxies outside the local group. And in sort of different regime in terms of the stellar mass, the environment, and distance. Okay, so we thought that we would start with sort of three key questions that motivate our work. The first one is that much of the work in regards to satellite galaxies in the last 10 or 20 years was done by the Milky Way satellites, which makes a lot of sense because they're very accessible. So we by now know the census pretty well and the dynamics and other properties. And I think we're going to hear about it in the next talk about how we use this information to inform models of galaxy halo connection using these satellites. But one very clear question is that the Milky Way dwarfs might not be representative, and we want to try and expand our search and our information to other Milky Way-like hosts and their satellite population. The second question, which is also very much related to this conference, is what's going on at the low mass end of the stellar to halo mass relation. We already saw this plot from Wechsler and Tinker review from 2018. And in particular, we want to try and provide data to constrain this relation, both for satellite galaxies, but also for field galaxies. So in order to have field galaxies that are that low, we need to search outside the local group. And then once we have such a sample, we would like and try and learn something about the physical properties of such galaxies, again, outside the local group. So whether they lie on the same scaling relation, for example, the size luminosity relation, but also what is their data mass. I'll talk more about that. So what is observationally needed? For the first key question, we'd like to look at other galaxy groups and study their. We're interested in the sample of the low mass galaxies, so again, beyond the local group, but actually down to pretty low masses, so stellar masses of 10 to the 5, 10 to the 6 solar masses. And eventually, which is also a very complicated task, we would like to try and have some imaging spectroscopic follow-up to measure other physical properties of individual systems, like their distance, the kinematic and stellar populations. The issue is that this is pretty difficult because, at least as we know them from the local group, low mass galaxies or dwarf galaxies in the local group are extremely low in surface brightness. So in this figure here from Josh Simon's review, we see the absolute magnitude on the y-axis is a function of size, and the diagonal lines here are constant surface brightness. You can see that many of the dwarf galaxies sort of occupy this area here between 27 and 30 or 31 magnitudes per squared arc seconds. This is extremely faint and difficult to detect even inside the local group, but let alone outside the local group. So what do we do after all? We are going to have this figure along the talk, sort of showing the different areas in this parameter space, and each one of us is going to talk about slightly different area. So I think we all know that in the local group, we are using the star count method. So we are detecting galaxies star by star using stellar kinematics. So the occupies this area here. Now in this figure, we see what's the distance we can detect low mass galaxies. So as a function here of the stellar mass. So these are these things here, which are pretty efficiently detected using star counts. So these are just two examples for sort of limiting magnitudes in different surveys. But once we go beyond the local group, we don't detect individual stars anymore. So Scott and I are going to talk about sort of on these two areas here when we go to the local volume and slightly beyond, so 3 to 20 megaparsec. And when we look at these distances, we're going to need integrated light detection. So galaxies are going to look like faint blobs on the sky. We're going to need high resolution imaging and kinematics of the stellar light to study something about their physical properties. If we go even further away, that becomes even harder, and what we need to do is, again, to detect these galaxies as integrated light objects, but then we'll also need spectroscopy, and we'll hear about it more from Marla. 100 megaparsec, usually photosys. But as I mentioned at the beginning, you see that what means low mass for one person, say people that study Milky Way satellites, will probably immediately think about ultra-faint dwarfs, which are somewhere here. For me, I would think about, and Scott will think about 10 to the 6, 10 to the 7 solar mass, and Marla will talk about even slightly higher mass galaxies. Okay, so I'll start. I've been involved with the Dragonfly project. I think you have probably heard about it, and also probably from me, as I gave a lot of talks in the last year. So just briefly say that this is a telescope that is built out of telephoto lenses. These are commercial lenses that we buy on Amazon. And the idea here is that each one of these lenses basically serves as a tiny refractor telescope. Okay, it has this special coating. The optics really is superior, and it's great. But what we do is that we arrange them in this mosaic design, and by doing that, we increase the aperture of our refractor telescope. So I think that what you should know, if you're interested in some numbers, is that Dragonfly in its current configuration, 48 lenses, is a 1 meter telescope. Refractor telescope with a focal ratio of 0.4. And if you really want to go simple, you should just know that it's optimized in precisely detecting pretty big and diffuse stuff. That's why when we looked at galaxy groups beyond our local group, so galaxy groups sort of between 6 and 20 megaparsec, and also the comet cluster, we were kind of looking for actually things that are not galaxies, but so in the Dragonfly Nearby Galaxy survey, we're looking for stellar halos of these massive galaxies here in the center. And in the comet cluster, we're looking actually for the intra-cluster light. But what stood out and sort of distracted us in a good way was that in both surveys, we found all of these very low surface brightness big galaxies. So we often call them ultra-diffuse galaxies. The name doesn't really matter. These galaxies are big. Their stellar distribution is pretty big, spread out on larger sizes than dwarf galaxies, and they are low surface brightness. Another way to think about it is that these are galaxies that have stellar masses of dwarf galaxies, but they have sizes of Milky Way galaxies. So just in case you've never seen one, I'll just show you. Here is the Dragonfly image of the comet cluster, just a tiny piece, and it's kind of hard to point out which ones out of all of these blobs here are actually these faint big galaxies. So I'll just help you. Once we subtract and sort of mask the high surface brightness signal, we're left with a few things here. So here are two of them that we discovered to be these ultra-diffuse galaxies, and these are HST images. Now you might notice that both of them have a lot of these very compact, bright dots. Ultra-diffuse galaxies also have pretty high number of dwarf clusters for their stellar mass compared to normal dwarf galaxies. And just sort of to put it to scale, here is the Fornax dwarf galaxy as we know from the local group on the same scale. And you can see that these ultra-diffuse galaxies are just some kind of gigantic dwarf galaxy that is just really, really big, but has sort of similar stellar masses. So, so again, these things are big and faint, and many of them have roughly 5 to 7 more globular clusters than dwarf galaxies with the same luminosity. And honestly, they are just like currently observed in all imaging data sets and all environments. So just wanted to mention a few. So for example, in this by Vanderberg from 2017, they found thousands of them in 8 galaxy clusters using CFHT data. In this paper by Tony Greco from 2018, using the HST survey, 200 square degrees, and this is also part of a much bigger more statistics from this survey coming up, I think. And then more recently, using DCAM data by Zaritsky, 300 of these galaxies in roughly 300 square degrees around the Coma cluster. So they're definitely a non-negligible population, and we're interested in studying them. So this also sort of already was kind of already known in the last conference, but I think that what happened since then is that we started thinking about what kind of dark matter, thinking and measuring, trying to measure at least, what kind of dark matter halos these things live in. And so here is the total mass to light ratio as a function of total luminosity within the half-light radius. And here are normal galaxies will be dark matter dominated, so they are sort of here. They have a lot of dark mass to light ratio is high. Also galaxy clusters, and we know we have this famous U-shaped curve. So people started measuring the kinematics of ultra diffuse galaxies, often by measuring velocities of globular clusters, because they trace, we think, the gravitational potential well. So a lot of the results looked like for many of these ultra diffuse galaxies, they are sort of they are dark matter dominated within the half-light radius. This is still a correct statement. Here are some examples. So here is by Beasley, a galaxy in the Virgo cluster. So you see all of these globular clusters. They actually measure the clusters. Here is Dragonfly 44. It's the Coma cluster. And in this case, we actually measured the stellar dispersion using light field. But what happened about a year ago is that even like it's not enough that we have sort of a pretty big scatter here, we also found these 2 data points, these 2 galaxies, DF2 and DF4, they are both in the NGC 1052 group, seems to have very, very low fraction of dark matter within the half-light radius. And you can see that their mass-to-light ratio is sort of consistent with 1, which means not too much dark matter. Okay, I think I'm gonna skip this part because I've heard Yao Q. So I just mention one more sort of future important direction that we're going towards with data from Dragonfly. So back in 2018, we did calculation to try and understand if we want to constrain the field mass function. Okay, so again, beyond the local group, down to 10 to the 5 solar mass, whether it's going to be impossible if we run a survey with Dragonfly. And we calculated that if we have some limiting surface brightness, say of 29 or 30, and some spatial resolution of 3, we're going to be able to detect galaxies down to 10 to the 5 solar mass for their stellar mass out to 10 megaparsec. So we hope that our calculation was correct because we ran this pretty big survey, 300 square degrees in the gamma and stripe 82 field. This is the Dragonfly wide field survey that we completed. And we already ran some tests on the data, and we're pretty happy with our limiting surface brightness. We think that we are now searching for these low mass field galaxies, and we think that it's gonna enable us to actually put constraints on the field dwarf luminosity function down to the numbers that we predicted just based on how the imaging data looks like. And I think my time is done, so I'll hand it to Scott.
Thank you, Shany. My name is Scott. I'm a graduate student at Princeton. Oh, Shany, could you keep?
Oops. Oh, yeah, I didn't mean to that. I'm sorry.
No worries. Anyway, so my name is Scott. I'm a graduate student at Princeton, and I'll be talking to you about a pretty similar mass regime and also distance regime as Shany, but it's a complementary project with slightly different science goals. If you go to the next one. Perfect. Yeah, so I'll be talking about recent progress in mapping the low surface brightness and low mass satellite systems in the local volume. This is the cumulative effort of both myself and also numerous groups, some of which are listed here. And then in the background image is some of these low mass satellites that we've been characterizing. And as you could see and harken back to what Shany was saying, these things are both very faint and also very low surface brightness. So it's a difficult observational challenge. But actually detecting these things is really only half the battle. It's actually much worse than that. Because the other hurdle is you have to somehow determine the distance to these things to be able to confirm that they're actually a physical satellite of a certain host and not just some random background contaminant. And customarily, this has been done through either somehow getting a redshift for one of these things or using Hubble Space Telescope to get a tip of the red giant branch distance. Either which is turns out to be pretty difficult and expensive, and so this introduces a bottleneck to the process and really slows down progress. But with that said, there's been a lot of work done over the last few years, and I think a statistical sample of hosts that have been well surveyed and well characterized is starting to emerge to the point that I think we can start answering some pretty interesting questions. And some of these early results is what I hope to mainly discuss with you all, in addition to some of our plans to continue expanding this sample. All right, next slide, please. Okay, so our project, we're calling it the Local Volume Satellite SBF Survey. It has the explicit goal to survey all satellites around sort of Milky Way-like things and more massive in a volume-limited sample, so the local volume, through the classical satellite regime. So we're talking down to satellite luminosities of maybe -9 or so in absolute V-band magnitude. And these two plots here show the current status of the survey. The colored plots are the hosts. So each point is a host. One of these local volume hosts is about 30 or so. The ones in color are the ones that have been surveyed, and the gray ones are the ones that we haven't looked at yet. And you can see that, while fairly few hosts have been surveyed all the way out to their virial radius, we're taking, a fiducial 300 kpc for hosts of this mass. Actually, a pretty good number now have been surveyed out to about half this, a majority, maybe 2/3 or so of the full volume limited sample. Okay. Yeah, so I won't talk too much about the nitty-gritty details of how we actually conduct these surveys. But just suffice to say that the candidates are cataloged using special detection algorithms that are specialized for low surface brightness object detection in various deep and wide field imaging data sets, and then are confirmed as actual physical satellites via some sort of distance measurement, whether it's tip of the red giant branch or redshift, or I'll emphasize surface brightness fluctuations, or SBF, which has really been our bread and butter in this endeavor. And we think that SBF has a potential to be a very efficient distance measurement and really rapidly progress or rapidly increase the progress in this area. I won't go into any more detail about how this distance measurement works or how we implement it, but if you are interested, I'll refer you to some papers we've done. Final thing I'll say is that all the results so far have been done using either archival data or various public imaging data sets from a lot of these wide field imagers around the world, like VCAM at CTIO, or MegaCam on the CFHT, and also HyperSupremeCam on SuGroup. These have been the real workhorses that have really facilitated this whole research area. Okay, next slide, please. Okay, so now on to some of our results. First, just looking at satellite abundance. So here we're plotting the number of satellites down to -9 in absolute magnitude, and also within a fixed 150 kpc of the host, versus host stellar mass. And then the full observed sample of the current progress of the survey is shown in the red points. And then the background color map shows the results from simulations. Here we're taking analogous hosts from the TNG simulations and satellites from the subhalo catalogs, and then using the stellar to halo mass relation from Garrison Kimmel et al. 2017 to assign stellar mass to these subhalos. And I'll emphasize two things here. One is that you can see that the Milky Way, which is given by the star, is really, appears to be quite typical in terms of satellite abundance compared to the nearby analogous systems. You can see it's really kind of right in the center of that clump there. And as Shany was saying in the introduction, putting the Milky Way in context is one of the really basic driving goals of this whole research endeavor. And I think it's neat that we're finally really being able to do that. And the second thing I'll emphasize is that the stellar to halo mass relation, without tweaking either the slope or the scatter, it seems to reproduce this trend between, reproduce this trend between satellite number and stellar mass quite well. And also the host-host scatter, which we were showing on the right panel here, which is just satellite abundance corrected for that general trend that shown by the purple line. This is just qualitative, but quantitative, we also show that the host-host scatter, the observed host-host scatter is pretty well reproduced by the simulations. Okay, Shany, next slide, please. So the overall abundance seems to be well matched by the simulation, but the actual detailed shape of the luminosity function a little bit less so. So here we're showing number of satellites, the average number of satellites per host in each of these magnitude bins. And you see that really no matter what slope we choose in the stellar to halo mass relation, there's a bit of a surplus of bright satellites and a bit of a deficit of faint satellites compared to the simulations. And I don't really know exactly what this means per se, but I think one takeaway is that it is clear that the statistics now for these local volume satellite systems is getting to the point that I think we can start putting interesting constraints on the stellar to halo mass relation, in a complementary fashion to the constraints that are placed from observed abundance of the Milky Way ultra faints. Like I presume we'll hear about more in the next talk from Ethan. Okay, next slide, please. Okay, so this is the final thing I'll talk about. Is a sort of odd result that we weren't really expecting, and I honestly don't really know how to interpret at this point, and that's the radial distribution of satellites. So shown here in the blue is the observed radial distribution for each of these hosts that we surveyed, and then in orange is the analogous simulated hosts that have been forward modeled through the observational selection function of for each of these observed hosts. And you can convince yourself that that there's a suspicious number of these that are too centrally concentrated compared to the simulations. Next slide, please. It just another plot pops up. Yes, and so here we're just showing that an ensemble, just a histogram of the projected separation of these satellites, and you can see that for the observed systems, they are systematically shifted to smaller projected separation from the host, and either now we're comparing to two different simulation suites. We don't really know how to interpret this at this point. We don't think it's too crazy because it's been known for the Milky Way that its satellites are more centrally concentrated than is typical for massive subhalos in simulations. And I think we're really just showing that that's, the Milky Way is not really atypical in this regard, that a lot of other nearby systems are showing this too. But exactly what this means, it's still not clear. And then with that, next slide, please. With that, I will pass the torch to Marla to tell us exciting things about the SAGA survey.
Awesome. Thanks, Scott. Next slide, please. So I am excited to give you an update on the SAGA survey. So SAGA is it's a small team. I think the majority of the team is on the Zoom call right now. And we've chosen to answer some of the similar questions that Scott and Shany have been doing, but from a much more statistical approach. And we want to characterize the satellite systems around Milky Way-like hosts, around 100 Milky Way-like hosts. The number 100 is to try and get some handle on scatter in many of those relationships. And in order to get 100 hosts, we needed to go out to larger volumes. So we need to go out to something like 40 megaparsecs. In order to do that, we no longer have access to the surface brightness fluctuation methods to do distances. And so much of what we have been doing is trying to increase our efficiency at finding low redshift satellite objects in a full spectroscopic survey. And so we're trying to get down to roughly -12, which is stellar mass of 10 to the 6, 10 to the 7. And that gets us down to about R of 21 at 30 megaparsecs. So next slide, please. So here's just a visual of our progress so far. So the last KITP meeting, the Galaxy Halo Connection, we had submitted a paper with 8 complete hosts using SDSS coverage. I think it was 39 seconds before the talk that I gave at that conference. We'd hope to do the same at this conference. The second paper, Yao will be leading. That should be on archive in the next couple of weeks. We've expanded our photometric coverage, so now we use both decals and DES for spectroscopic targeting, and we have 36 complete hosts that we will be reporting on. Next slide. Just this will be a quick visual on how we have improved our targeting. Next slide, please. There we go. The left panel, we're showing just the spectroscopic redshift distribution of all targets around, basically around a host. This is the number of targets per square degree, but that's roughly one host. Paper 1, we were using very basic GRI cuts, which is the light blue, just giving you a sense of how many targets we have to get per host. We are now able to get what we believe is complete, or we understand our incompleteness, with about 200 or 300 targets per host, which allows us to reasonably get to 100 hosts in the next few years. In the 36 hosts that we'll be publishing soon, we've identified 108 satellites. We are certainly missing a few satellites, but we think we understand the ones that we are missing. And the satellite ranges in the stellar mass between, our lowest one is 10 to the 5 or so, up to 10 to the 9. So next slide. So just briefly showing the results. I won't actually go into the luminosity function number of satellites, but this is from paper 1, the luminosity function and the number of satellites as a function of absolute K-band. In paper 2, with 36 hosts, we get to use a lot more colors in the rainbow. But you can also see that we see a real diversity in the luminosity function. So we have 4 hosts we feel are complete with no satellites down to our limits. Where we also have objects where we have 9 or 10 satellites, where the Milky Way has 4 or 5. And so just looking at the number of satellites as a function of K-band, we still see a trend where more luminous hosts have more satellites. And we'll be exploring these trends in the paper and comparing, obviously, to models. The result that I wanted to spend 2 minutes on is in the next slide. So this is looking at the quench fractions of satellites. So in this plot is the absolute luminosity of a satellite as a function of its G minus R color. And then the points are color-coded by our spectroscopic measurements, where we call a galaxy quenched if we don't see H-alpha emission. And so in our paper 1, we had this odd result where 1 of 26 satellites were quenched, and you can see that 1 red dot there. In comparison, the Milky Way has 2 of 5 satellites that are quenched, and so it was different than the Milky Way. In the larger sample, that still holds, but now we understand this result more. So in paper 2, we now see 14 of 108 satellites are quenched. But what's amazing is that all 14 of those satellites are faint. That is, all 14 quenched satellites are fainter than -16 or something like -10, 10 to the 8th stellar mass. And so looking in the right panel, this is the quenched fraction as a function of stellar mass. In the field for isolated galaxies, that's the purple line as a result we had from 2012, where the quench fraction decreases as you go to lower stellar mass. And at least in SDSS, we see no quenched galaxies below 10 to the 9. In the Milky Way M31, the opposite is true, where we see star-forming satellites, LMC, SMC at 10 to the 9, and then we see all quenched satellites towards lower stellar masses. And SAGA seems to be sitting somewhere in the middle. So we are seeing quenched satellites at our lowest stellar mass bins, but much more star-forming satellites in the larger bins. This is in line with predictions from hydrodynamic simulations, but we're really excited about this result. I will now turn it back over to Scott to conclude.
Okay, thank you. Shany, could you go to the next slide?
Yeah, sorry, it's just I think the delay. I do that and then
okay,
it takes
no
like
worries,
2
no
seconds.
worries.
I don't know. Can you see it? Because I see.
I'm still on quench fraction.
We're so excited about quench fractions, we don't want to keep going.
Ooh. Now, that's weird. Let me do that again. Okay, is it okay?
Perfect. Yeah. Perfect. So I'll just very briefly kind of summarize here because I think we're about out of time. A lot of the progress that's been done in the last couple of years is really indebted to the availability of these very wide field imagers. We talked about the DRAGONFLY project, also HyperSpringCam on Subaru, MegaCam on CFHT, and DCAM. They've really been the workhorses that have been, allowed the discovery of low surface brightness objects in a variety of different environments and have allowed us to build the statistics that I think we can start and asking very interesting questions. And then looking forward to the future, I think that the shift in new instruments is maybe a little bit more towards the spectroscopic side. And there's some really advanced or really impressive integral field instruments, KZWI on Keck, and then MUSE from the Europeans, that I think in the future will have a very big impact on allowing us to measure kinematics of these things, like we've done for the satellites of the Milky Way and Andromeda, but now at extragalactic distances. Again, we're increasing our statistics. I won't talk too much about each of these upcoming surveys. I think it goes without saying that LSST from the Vera Rubin Observatory will really usher in a new era for low surface brightness galaxies and building statistics of samples of both satellite low surface brightness galaxies and also galaxies in the field. And follow up, we talked about this. It's in the past has been a big roadblock and is partly or one of the causes of why this has been a difficult endeavor to do. And finally, connecting to models, I think we'll hear much more about this in the next section, in the next talk. So I won't go into too much detail. And then next slide, please, Shany. I think there's just a summary slide. And with that, we'll leave this up and love to take any questions.
Can you see it, the summary slide?
Yes, I can see it. Perfect.
Thank you. All right. Let's see if we got some question. Andre, do you want to ask your question live?
Yes, sure. Thank you for wonderful, interesting talks. I had a question the main question for Scott that I have was how generic you think the concentrated radial distribution of satellites is, because in the figures, when I read the paper, it seemed like it's kind of intermittent. Like in some hosts, like Milky Way, it's concentrated, and others it seems to be fairly consistent with predictions. The point, if I got your point right, it seemed like you were presenting that this is something generic, but I wonder whether it's actually generic or rather occasional feature of particular hosts that may reflect some feature of the evolution.
That is a good question, and honestly, at this point, I don't think we really know. So, from what we had in the paper to what we have now, we do have more hosts, and it seems that this general trend of being the observed systems are more essentially concentrated does seem to hold. But like you said, some hosts are totally normal. We've noticed that in general, it's the more massive hosts, things that are distinctly more massive than the Milky Way. In this plot here, it's the bottom row. These things are more like loose groups. And then you can see that they are much more, they follow the simulation predictions much better. And it's these, obviously the Milky Way and then some other very Milky Way-like galaxies like M101, NGC 4258 that we do show this. Honestly, though, with the local volume, we still don't have all that good statistics. I think this is something that's would be very interesting to look at with the SAGA survey too, with those extra statistics.
Yeah, and so just to put a spinner in this, going out to 300 megaparsecs, we are seeing on average that the satellites are less centrally concentrated compared to the Milky Way.
Okay, yeah, this is interesting. Yeah, I think this is definitely exciting work to be done here.
Thank you.
Alice, I just want to see if you want to chime in on the simulation comment that you had.
Yeah, sure. This was a question to Scott related to this, but you had a different plot that showed the histogram of distributions as a function of radius. Right, this one. So it doesn't surprise me necessarily that the observations are more centrally concentrated, because I do believe that a lot of small satellites fall out of the catalog as they get stripped and are artificially, I guess you'd call it artificially disrupted in the simulations. It's the excess that I find interesting at large radii. Do you, is it you know, possibly that you're missing some? I know you think you're complete to 150 kiloparsecs. Can you comment on that at all?
Sure. So that is, yeah, that's a good point. I should have been. I think that's mostly an artifact of specifically how I'm plotting this, because we're not using a stellar to halo mass relation in this case to assign stellar masses to the subhalos, because these are not hydro results; these are only dark matter only simulations. But with a disk in the case of Fat Elvis, but we're just taking the same number of the same number of the most massive subhalos from the simulations as the analogous as what we're observing. So like the area under these histograms is constrained to be the same. So that was just a way of plotting this.
Okay, thank you.
I think Phil and Aaron both have a question that are related on the quench fraction. If one of you want to just unmute, I think both of you can unmute yourself.
Okay, I'll ask my question. So the question was, Marla, in your talk, you compared against Milky Way and M31 for the quench fraction. But since we have like this amazing set of highly resolved satellite systems in the local volume now, do you know how the local volume would sort of shape up if you put it in this right-hand plot?
That's a good question. We have not yet compared to local volume, and I don't know what the answer will be there.
If I could say one thing, an issue with that is for a lot of our local volume satellites, we don't have spectra. So, and we can maybe say if they're quenched based on color or whether they're, you know, by morphology, but it would be sort of apples to oranges because we don't have spectra for a lot of these things. But that's something that I think we're also interested in checking out too.
Okay, cool.
Okay, so I'll ask my question, which is, wonder what the prospects are for the quenching fraction in a field. Is that known below about 10 to the 8th stellar mass, or are we waiting for follow-up to the DRAGONFLY survey? What are the best prospects on that?
So there we really need statistics. So the purple line actually goes down to, I think, 7.5 on that plot. That's from STSS, and we need that volume in order to find satellites that are in the field. And so that is going to require something like DESI bright time survey to be able to survey a sufficient volume and get distances to find the isolated low mass galaxies.
I'll just add one more thing. So another survey which I didn't talk about is an ultra-wide survey with DRAGONFLY that Johnny Greco is mostly leading. So this is going to survey the entire, we already started, we're surveying the entire Sloan footprint, so roughly 12,000 square degrees. So it's also one of the motivating questions actually for this survey. So hopefully it's not as deep as the wide field survey because it's just very big, but hopefully we're gonna add a little bit more to this area with this survey. It's like 15% complete so far. It should be completed in the next year and a half or so.
Annalisa, do you want to ask your question?
Yes, guys, if there's time. It's a question, comment for Scott, and also related to the comments earlier about the radial distribution. So indeed, Scott, thank you for specifying. The comparison that you put in your paper is from a dark matter-only simulation, which is somehow painted with galaxies. And so can you please remind us, so you are assuming that the ranking of the subhalos is the same as the ranking from most massive to low masses, essentially, no? Of
that is
satellites.
absolutely correct, yeah.
And this is also for, say, the radial distribution. We are assuming that the satellites have the same radial distribution of subhalos, which is probably not the case when we actually compare this from full physics to dark matter-only simulations. And so,
that is true. So we were thinking that at least for these very massive satellites, like classicals and above, that assumption should hold true. I think certainly for ultra faints, where you have things like reionization and that sort of physics start to matter, that I think a bias could be introduced.
I agree, but indeed, so this is, I would love to hear more from our participants today, because the subhalo halo connection, the galaxy halo connection at this low mass end is incredibly tricky, because it's convolved with the stochasticity of star formation. So below subhalos are 10 to the 10 solar masses, and we are talking about 10 to the 6, 10 to the 7 solar masses stars. Some of them start not to host galaxies, and so then you start to have the flipping of ranking.
That's a good point, for sure.
Also
definitely needs
probably at these masses. Yeah. Thank you, guys.
All right. Thank you all the speakers and questions.